before moving ahead and constructing the free particle propagator using this formalism, I will elaborate a little bit on the implication concerning the sum over the all possible paths. Perhaps that picture may be needed. I will retain it. And I will draw a picture, again, taking advantage of using one-dimensional formulation, because it's higher dimensional, I cannot plot it on a two-dimensional board. Okay, the picture I would like to depict is the following. Now here is the time axis. This one is the space axis, right? Here's the time. I will start with T0. Usually it's going to be taken 0. That's the reason why I start from here. That is T1. And that is T2. I think it's sufficient. Then I can move to generic. This one is Tk minus 1 and Tk, because that's the notation I used, Tk. And finally, I am at Tn minus 1 and Tn, which is the final T, right? The final T. This is the initial and fixed. Initial and final points are fixed, so therefore, let me use a notation to indicate that this is the initial time, final time. This is the label I used to denote the initial and final. I could have used different labels. Suppose I have started from here. Again, use it with color to indicate that it's a fixed thing, and the intermediate ones are not fixed. So how did we really proceed? We proceeded like this and like this. And perhaps from then on, again, some zigzags. Go to this generic one. They have gone all the way there. Then, from there on, I may have moved in this direction. And then again, after this transition between this generic thing, I might have moved again all the way to up Tn, through several steps. I am skipping those intermediate steps, depicting the generic one in the middle and some of them in the beginning, because this is Tk minus 1 Tk, Tn minus 1 and Tn the final, and coming here and making this final transition to that fixed point. Okay, this is T0, and this location is x0, T0. That state associated with this point, perhaps, again, color is needed. That's the fixed initial, x0, T0. That is in this two-dimensional configuration space, my particle is at a position x0 at time T0, and it has moved to x1, T1. Then it has moved to x2, T2, and it has moved eventually to this point, which is xk minus 1, tk minus 1, and moved up xk to tk, and finally, to use the proper label, xn, tn, which is really, in my notation, xn, t. But the point is that if you remember the insertion of the completeness identities between the very final and very initial at the subdividers, here are the insertions. An insertion at T1, an insertion at T2, insertion at T3, involving integrations. So these points are not fixed variables. You're integrating here over the x1. You're integrating over the x2, and so on. finally dx and minus 1. The final is fixed, you are not touching. So these points, in principle, are infinitely many. If you don't integrate over anything, if you integrate over one of them subdividers, so you can have different paths, right? You can go like that, you can go like that, you can go like that, go like that, and go like that. At even one layer, when you are integrating over the x1, you are really thinking of all these possible transitions at this point, infinitely many. So the infinitude is a horrendous infinitude. And then you do the same. Once you have reached to this via these infinitely many zigzags, infinitely many, then here also you start zigzagging infinitely many by integrating. So at the end of the day, what is happening is that if you really plot that picture from here to there, this is the t0 time axis, and this is the tn time axis, and that's the initial point which is fixed, and that's the final point which is fixed. And what are all the possible paths? You see what I mean? Because of this mathematical integration, what that expression means is that it is not this thing only, as triggered Feynman's beautiful attention. That's, well, there was some proper normalization, of course, single thing, but it is the sum of, it is the sum of. Did I write it somewhere? Yes, probably I did. Yeah, outside, right? It's the, what is it? Let me copy it in here, and then it is this thing, right? The x e to the I over h bar t0 to t dt prime L x and x dot. Perhaps, yeah, x dot. Prime is the derivative. That's the expression. And all the sums over all paths are buried into this. And I write what that measure is right here. Infinitely many. So there are so many paths, and the measure, this measure is complicated. And thereafter Feynman has discovered this in his thesis, then eventually for quite some time, till it was adapted and used, being incorporated into the research curriculum, there have been many mathematical works on it, particularly focusing on understanding the measures. And some prominent mathematical physicists and mathematicians have really written valuable papers on the meaning of this Feynman's measure, integral measure. Measures, well, those of you who are mathematically oriented, you know that measure is a difficult subject in its own right, right? Probably you have seen a little bit of it in the calculus, advanced calculus courses. This is, of course, orders of magnitude more difficult, but beautiful, really. This formalism is aesthetically so beautiful. And for example, at some point you may wish to discuss and to try to have a feeling, and as these x's are covering entire spectrum, how does this result reduces to the Feynman original Dirac's version of the classical, the classical one, when h bar goes to 0. In the classical limit, it should reduce to that particular limit, right? E to the I over h bar as classical. Try to think on your own. You won't be responsible of this in the exams because it's a difficult subject. But for those of you who are thinking for the future as a research, little exercise into the research, you may wish to play on it on your own. So we are at a good point now, which is the usage of this expression, Feynman's version, to construct the free particle propagator via this, because the other version we have seen already, right? Okay. If you allow me, I'm planning to do the following. Let's start and finish this problem, this discussion of the construction of the free particle propagator, and let's stop at that point. Instead of giving another break at 4:30, it may last and prolong a little bit, so that we finish the subject and we quit for the day. All of us, we may save some time this way, I guess. So subject is free particle propagator in Feynman's path integral approach. You know the result already. We have done it directly. It was an easy result. Let me not copy it. We know what we are talking about. Okay, so what is the free particle Hamiltonian? Or Lagrangian, really? L is, let me do it again in one dimension for simplicity, not to make the already complicated looking expression more complicated. I hate to use more ugly, well, because there would be too many indices floating around. So this is the Lagrangian, right? Because Lagrangian is kinetic energy minus the potential energy. Free particle means there is no force, no potential. It is purely the kinetic energy term. So it's going to be this expression which we are going to use in the expression that I have erased, okay? Let me introduce a set of notations simplifying the, I will take the initial time to be 0 for simplicity instead of carrying over t minus t0, and I will take the final time to be t so that I can use this t final, t initial. I can use the ordinary t without primes for the generic integrations because I want to simplify the notation because you'll see why I need that simplification. Okay, so k x t, and let me see whether I have reserved any notation for the final one. It's k, okay, x0. Again, let me see whether I have anything. No, I use the 0, keep using it. x0, 0. So that is the, x is the final, x0 is the initial position, t is the span of time. It's nice to describe the entire interval with a capital T by choosing the initial time to be 0, okay? So I will have then d Feynman measure x, e to the I over h bar, 0 to t dt 1/2 m x dot square, right? That's the exponent. And let me work out the exponent first and then the measure. Exponent is easy to work out, right? So it is the dtl is, how do I write that integral? I write that integral as I to n epsilon 1/2 m xi minus 1 divided by ti minus 1 squared. That's the definition of the velocity. And take it at a generic position and then sum over all intervals, 1 to n. Well, we have defined that infinitesimal generic intervals as epsilon, so that t is n times epsilon, or epsilon is t over n, because t is the final time minus the initial time. And so there is an 1 over epsilon squared coming out. So I take that out, 1 over epsilon squared and epsilon, so it is m over twice epsilon times I from 1 to n xi minus 1 squared. So this line integral from 0 to t at the exponent is expressed in such a nice form, nice and simple form, really. Of course, when I put it in the action, there will be an I over h bar in the front as well. Okay, so let me write it that way. I over h bar dtl. You see the advantage of, now I'm not going to use the t prime or anything. T is the now generic integral. The final and as initial points are 0 and t. So this will be then I m over 2h bar epsilon I from 1 to n xi minus 1 squared. So that has become really nice. In order to make it even nicer, I will introduce a new variable now, make a variable change, employing this portion. It already suggests me, I leave the I out, I need that I write m over 2h bar epsilon x squared for any I, x1, x3, or x27, doesn't matter. I define that as a new variable, u squared. Okay, so how about the measures? Because I had in the integral, I have to work the integral measure a little bit, perhaps, at that point. But as a preparation towards that end, let me write this as x is 2h bar epsilon divided by m times u, or dx is this factors times du. You'll see why I need to do such simplifications, because measures are, remember, the measure was horrendous. Okay, let me write the measure now. What was the measure? Dx. This was limit n going to infinity, m divided by 2 pi h bar I epsilon to the n over 2 times I from 1 to n minus 1. How many subdividers? 1 to n minus 1, number of interval is n. Therefore, in that exponent, there is n appearing, but in the measure, there is n minus 1 appearing, right? Okay, that's nice. Times dxi. I will rewrite this in slightly different fashion to make everything look nice. Now I will write underneath. Limit n goes to infinity is still there. I leave this one of them out, 2 pi h bar I epsilon. Move the remaining inside to n minus 1. N minus 1, I equals from 1 dxi times m over 2 pi h bar I epsilon. Okay. Putting this into this, meaning that there was m minus 1 over 2, one of them I left out. It is this factor for each dxi. For each dxi entering into the integral, there is this factor, but there is one odd man out, which is pushed. As I said, some people get very upset and therefore they ignore it, they drop it. When they drop it, there is no chance that they can get the correct result. They don't know this, however. Anyway, so it is there. So I have really managed to decompose my Feynman path integral expression for the transition amplitude into the necessary parts. So let me start writing it and recursively start computing it. This recursion technique in itself is quite nice. So it is not only the result, but the methodology I am teaching you. For example, if you face the challenge of using this expression for a more complicated problem like harmonic oscillator, you have to use this algorithm, and using this algorithm is not an easy one. So this will be quite a good warning, I presume. Now let's see what this variable change I have done. I have to change the x's to u's, right? Is this, if this is visible, I would like to do it next to this so that I don't mix up the notation. So what is the dxi? Dxi is this factors times the du. So dxi times m divided by 2 pi h bar I epsilon is, if I write this dxi from here as 2 h bar epsilon divided by m times dui times this. This is equal to times m divided by 2 pi h bar I epsilon. Now 2h bar cancels, m cancels. What is left over is dui divided by pi, epsilon also cancels, I pi. That is, this entire thing, with that variable change I have carried out, reduces to this dui over I pi. So let me now start in here. What is the amplitude then is, k is limit n going to infinity. There is one extra factor which is left out, 2 pi h bar I epsilon times I, the picture is there, never forget this, from n minus I1 to n minus 1 times dui divided by I pi. You see, it's simplifying beautifully, really. Times, what is left over in here, after this variable change, this has become the u, right? So, exponential, sorry, e to the I, j 1 to n, although this is n minus 1, the number of intervals is n. Please never make a mistake in this counting. All of a sudden, you see it reduces to something which is quite a clean and manageable form. This is really the Feynman propagator for a free particle. All we have to do next is to carry out these integrals in a recursive and clean manner and carefully, right? There is n minus 1 dividers there, subdividers, and n intervals, which is reflected dividers, number of integrals, intervals, number of terms in this sum. How do we proceed in carrying this out? We have to do it recursively, starting from the integration 1 integration. So I will carry out as the first step u1 integration. Let me write it carefully so that you can really absorb this algorithm. This algorithm is an important one. Particularly, as I said, the algorithm is probably more important than anything else. To carry out the u1 integration, you notice that exponent is not that simple. How it goes? It goes in the following manner. J equals 1 to n minus 1, uj uj minus 1 squared contains what terms? It contains u1 minus u0 squared, u2 minus u1 squared, u3 minus u2 squared, all the way to the final point is n, un minus 1 squared. You say it's not a big deal, but you have to remember that the final point is fixed, and that is u really. You can drop this. That's x or u, which I labeled the final state. And originally, the initial one, I could have put an u sub I saying initial, but 0 I retain for counting. So you have to remember that these are reference points, really, which should survive at the end of the day. This will survive, and that will survive. All the rest are to be integrated out, because there are u1, u2, u3, un minus 1 integrals. This will survive, all the rest will be integrated out. You see how subtle that is. If we are going to carry out the u1 integration, perhaps I have to, for aesthetic reasons again, mathematically correct, let me expose this and then start the u1 integration, because this is independent of the order of integration, right? So the first step is u1 integration. Well, to carry out the u1 integration, I should label it with a different color. There's u1 in here, and u1 in here. So obviously, I have to combine these two terms and complete the full square, carry out the u1 integration, and retain the leftovers. Leftovers from these two, and then carry it over the next step to carry out the u2 integration. I will have u2 in here and some u2s coming from here. Combine them, carry out the u2 integration, and after a few steps, you'll see how it's going. The induction, right? Step by step. We will have the rule, thumb rule to proceed. But let me do patiently the first u1 integration. What are the terms that I have? I have u1 squared plus u0 squared minus 2u1 u0 plus u2 squared plus u1 squared minus 2u2 u1. These are the terms which I have from these two. Only these two involve u1, all the rest not. It looks a bit discouraging, right? You say, is it ugly? Well, let's get panicked. Let's proceed a little bit. You'll see that it's going to unfold cleanly. Again, let me resort to the help of u0. It is to be left out, of course. It's something fixed. I cannot do anything about this. It's out there. So u0 squared. And what are the u1 squared terms? There are two of them, 2u1 squared. And there are two other u1 terms, right? Minus 2 u1 u0 plus u2. Nice. This will be reserved, and u2 will be combined with the other thing which is coming out. And finally, there is the u2 squared term, which is to be retained. So what are the things out of this? What are the things out of this that I have to focus on? It is these two. As far as the u1 integration is concerned, this is going to travel all the way to the end. This will combine with the next. But I have to do something in here. What is that something? First of all, let me factor 2 and write it as u1 squared minus u1 u0 plus u2. You see, I'm preparing myself to do some tricks. Put a 2 in here, divide it by 2, so that you are psychologically preparing yourself for squaring, full squaring. Okay. Is it so? Indeed so. If I write it as u1 minus that combination squared, then I have to compensate with additional terms. Let me do it. So this is something I am carrying over. Let me not forget what I have there. Okay, so I have, first of all, I have the 0 squared plus u2 squared, which are this one and that one. I'm carrying this over here. And plus 2 minus, no, times u1 minus u0 plus u2 divided by 2 squared. Yeah, okay. What are the compensating terms? Here, let me write underneath, minus, because this is a plus square of the second term, u0 plus u2 squared. Fine, let me proceed. So I have twice u1 minus u0 plus u2, 2. Actually, I can write it something because the integrals over u1 or u2 or minus infinity to plus infinity, I can shift the variables without affecting the final ends, a minus infinity to plus infinity, but doesn't matter. Just to have the correct algorithm, let me carry it over, plus u0 squared plus u2 squared minus 1/2 u0 plus u2 squared. You say, why? That's a minus in here. There is an overall 2. Convert this to minus. I will carry out the u1 integration, but is there a simpler, nicer form of this leftover term? Perhaps I should write it in a form so that you have a nice feeling about this. I claim that this is 1/2 u0 minus u2 squared. Let's check immediately. Is this really so? u0 squared, u2 squared, minus u0, u2 twice so. Do I see them appearing in here? Yes, indeed so. Let's check. I will check it for once and leave the others for you. Is this, if I work it out, equal to this one? Let's check. u0 squared, there's an overall 1/2. Twice u0 squared, twice u2 squared, minus u0 squared, minus u2 squared, minus u0 u2, twice. u0 squared, u0 squared, 2u2 squared, minus 2. u0 squared, u2 squared, 1/2. Correct, right? I have indeed demonstrated that this leftover piece is 1/2 u0 minus u2 squared. Nature runs sometimes in such a beautiful manner that the beauty of the nature and the beauty of the aesthetics of the mathematics hand in hand. This leftover should come out to be in such a nice fashion is really a miracle, honestly. So what do I have then? Remember, I'm still here. This thing has become that plus that. This portion will be taken care of by the u1 integration. This is going to be carried over to the second step. Isn't that nice? Second step means it will be associated with this one. It contains u2, and that's the only other one in this sequence which contains 2. u2, that is. Okay, let me do it step by step. What is the result of this first integration? What are the integration measures? We have proven that integration measures are these beautiful things. There are m minus 1 of them. The u1 I pi times e to the, what were the exponents? We have retained the i's, right, in the exponents. Where is it? Yeah, there. We have retained the exponents, so it is I times a 2 in here, twice, u1 something minus something. That something doesn't concern me anymore because the integral limits are minus infinity to plus infinity. So I shift this to u1 bar, u1 twiddle. This is u1 twiddle. So it is du1 twiddle divided by square root of I pi e to the 2I u1 twiddle squared. Result? Result is 1 over I pi is already here, and the result of this is square root of pi divided by 2I, right? This is the alpha, this is twiddle, so it's not 2 or something. Alpha is this, square root of pi over alpha. So what do I have in here? What I have in here is pi over, is there a problem with the i's? Oh yeah, I made a mistake. An innocent mistake, but a serious mistake as well. Why? Because my Gaussian integral has a minus sign in the front. It is minus 2 over I. To make it minus, because the Gaussian e to the minus alpha times, indeed so. So it is 2 over I. You see, otherwise I would be getting an additional ugly i's. Now this I and that I kills nicely. Pi kills nicely. Result is 1 over 2. Wow, it's amazing, really. The u1 integration, I have to collect those as a stock somewhere. The integration started giving me numbers. The first integration gave me 1 over square root of 2, and a leftover piece, which I will combine with the second. We have to keep this in mind. Let's not forget this. This is the result of the first integration. And we'll already see how it's going, the systematics at the second step. Okay. Fine. Now let me go to the second step. Leftover is this one, and already existing U2 terms, right? U2 integration. So I'm interested in this U2 integration. The existing one is U2 minus U2 squared. There's a new U2 dependent term coming from here, 1 over U0 minus U2 squared. And let me elaborate and combine. This is equal to U3 squared plus U2 squared minus 2 U3 U2 plus 1/2 U0 squared plus 1/2 U2 squared minus U0 U2. Let me focus on the U2 terms. How many U2 terms I have? This one and that one. 3/2 U2 squared. This one and that one, minus U2, U0 plus 2U3. Okay, then these two. 1 over 2 U0 squared plus U3 squared. That's all. I have taken into account everything, right? And to complete the full square, what do I do first? If you allow me, I will use the eraser on the board and write this as, by putting in 2 by 3 in here. Right? It was minus 1 at first, so I have this result. Yes. I have to go controlled so that it's a dangerous business. We don't have to make any mistakes. So, okay, let me proceed now. I will rewrite this as 2 U2 U0 plus U3 twice U3 divided by 3. Yes, indeed so. Then I can complete it to a full square, this one, leaving the coefficient out. It's going to be U2 minus U0 plus U2 U3 divided by 3 squared. Compensate by subtracting this square of this thing, which is minus, square of this thing, right? This, which is minus 1 over 9 U0 plus 2 3 squared. Okay, let me combine my results and let's see whether I can express them in a nice fashion. First of all, I have 2 by 3 u2 minus something squared. I call it something because you see, because of the range of the integration, whatever that something is not important, I'll shift. There's a 3 and 3 kills, so minus 1 over 6 u0 plus 2u3 squared, this extra term, plus leftovers in here. Let me write the leftovers, 1/2 u0 squared plus u3 squared. So my next task is to try, as the first one is manageable, I can carry out the integration. The only difference from the previous one is this number in the front. It's not difficult to take care of. The only thing which I need to be very careful is what is that thing equal to. I will do it in here and then I will move to the left corner because I want to keep them under control. So what is that extra piece? Now let me demonstrate that that extra piece is also very simple, like 1/3 u3 minus u0 squared. The claim is that, I hope you can see it, this entire piece is amazing that nature arranges itself so nicely, u3 minus u0 squared. Hard to believe, right? But it's beautiful. How can you check? Well, the check should start from the bottom and show that it's indeed equal to the. Let's do that. Let's start from the bottom one. This is a check. I have written the result. I am doing a quick check for you. Minus 6 u0 squared, 4 u3 squared divided by minus 4 by 6, 2 by 3, u3 squared. There is a 4 and again 6, 2 minus 2 by 3, u0, u3, plus 1 over 2 u0 squared plus u3 squared. Correct? Correct. If I multiply this by 3, 3 minus 1 is 2, 2 divided by 6 is 1/3 u0 squared. And this is 1/3. Isn't that beautiful? 1/3 u3 squared. And minus 2/3 u0 u3. And that's the proof. So that gives you, let me write it where do I write this? Perhaps I should open a bracket in here, in the middle, yes, here perhaps. I have done the first one. The first one is encircled. We are at the second one. In the second one, I will have that expression. So we are still at the u2 integration. du2 divided by I pi e to the I times 2/3 u2 minus something squared plus that extra piece. Let me write that extra piece so that I will combine it with the others. Plus 1/3 u3 minus u0 squared. It's going to be carried over to the third step. What is this integral? Again, shift, call this u2 twiddle, convert this to u2 twiddle because of the infinite range of the integral, and write this as minus 2 by 3, 3i. I put the I down to get the Gaussian suppression factor. U2 bar squared. Then the integral then is 1 over I pi square root of pi divided by 2 over 3i. These i's nicely kill, and pi's nicely kill. I have 3 by 2. Correct? 1 over 2 by 3. 2 by 3. It was 3 by 2? 3 by 2. I copied it incorrectly. These are 3 by 2s, sorry. Wrongly copied. Sometimes that's very dangerous to try to do it in the board. It is 3 by 2. Nice. So it is 2 by 3. So that is as I said, at some point I thought I should have a logbook. The U1 integration, U1 int gave me what? 1 over square root of 2. U2 int gave me, well, this is already there, so 1 over 2 times the new one is 2/3. So at the end of the second step, I have 1 over square root of 2. At the end of first step, I have 1 over square root of 2. At the end of second step, I have 1 over square root of 3. At the end of third step, I have 1 over 4, and so on. So that's for you to really go ahead and check it. But this second systematic is also important. So at the end of, let me summarize this, because when you are using recursive type of arguments, you have to, at some point, list the results accordingly. This is not visible, I guess. At the end of first step, I had what leftovers? I'm going to write the leftovers, and then you'll see what I'm shooting at. I had 1 over 2 and e to the I u2 minus u0 squared, and everything else. At the end of second step, I had 1 over square root of 3, and left over e to the I 1 over I over 3 u3 minus u0 squared, and everything else, whatever left over. So it wouldn't be too far-fetched if I now start making inductions to be checked. I invite you to check a few more steps, third and fourth. So I claim now, at the end of third step, you'll have 1 over 4 e to the I 1 over 4 u4 minus u0 squared. You're really going over. At the end of n minus first step, what do I have? Third, fourth, second, 3, first, 1. So 1 over n e to the I over n un minus u0 squared. At the end of n minus first step, I am done. I have carried out all the integrations. So this is really the result, isn't it? Let's put everything together now. If we put everything together, to cut the long story short, I had at the k in the front this factor, and I was doing these integrals. So k is the limit n going to infinity m 2 pi h bar I epsilon, this ugly beast which was, you know, asymmetrically carried over. If I was a symmetric crazy guy, I would have dropped this, and if I dropped it, you see, I would have been in trouble indeed. So this is what I have, times this, times I over n, un, which is u, the last point is my final point, u minus u0, wow, that's it. These were the results that I was trying to get, right? But how about this, the expression in the front? There's both epsilon, which goes to 0, there is n, which goes to infinity, but they're really of the right form. What do I mean? If I put them together, what is this? T? I over n. Well, I am done. I'm not done yet because I have to take care of this. Let's go back to the original variables. The u back to x. What was the x in terms of the u? I erased this. If I can trace it back. What was it? Yes. Remember our definition, m over 2h bar epsilon x squared was u squared. Nice. If it wasn't so, we would be wondering what happens to this n. If n goes to infinity, I would get 0, wash out. But there's hideous, epsilon is hidden in here. So what is that u minus u0 squared is? M divided by 2h bar epsilon x minus x0 squared, right? If I substitute that in, then 1 over n u minus u0 squared is m times 2h bar n times epsilon. Isn't that great that everything fits so beautifully well? X0 squared. What is n times epsilon? It is t, right? So we are done. I can write the result, and we can really say that we have done a lot using Feynman's version to get the beautiful and correct result. Well, it's not that trivial, although steps are complicated. It's so gratifying that the algorithm works perfectly. All these convention and definition of the measures work perfectly, right? Otherwise, out of these complicated expressions, we wouldn't be surviving, I guess. T times e to the I over h bar, putting back all these numbers. There is an I, of course, in the front, this I over h bar, 1 over 2 m x minus x0 squared divided by t. Isn't that what we have obtained using simple reasoning? That is, borrowing the canonical commutation, the canonical quantization results, substituting it back into the explicit representation, then we have obtained this result. And we have checked that indeed they satisfy the beautiful rule that when t goes to t0, it goes to delta cube x minus x prime, etc. All those beautiful properties. Now we have been able to reach that result. And what is that? That's really the classical action, right? Indeed so. So it is really, this one is then e to the I over h bar as classical. Question. When you work it out, meaning you are using Feynman's path integral formulation, which is implicit, in which it is implicit that you are summing over all paths. Infinitude is very crowded, infinitely many paths. You still get that classical expression. What is special about the free particle? That when you compute the quantum propagator, Feynman's quantum propagator, you get the classical result. I invite you to reflect on it philosophically. I think it's a beautiful subject. That, I think, is a good point, given the fact that we have already spent so much time in the morning. Instead of starting a new subject like gauge theory in quantum mechanics, we could as well stop in here. And I think I have said everything I should say on the path integral formulation. And I also depicted the complications and subtleties of the algorithm, which Sakurai tried to avoid. I know why he has avoided this. To give such a complicated presentation in a graduate, even graduate course, it may not be that appropriate or even difficult for him, he must have thought. So next week, as we have now recovered our missed lecture, we are quite good on our program. I will spend the next week on discussing the gauge problem in quantum mechanics. I noticed that in certain years, the professors giving this course has skipped that, but I'm not going to skip it because one of the purposes of this class is to prepare you to do research. As you have seen, most of those things that we are going to cover after that, the angular momentum, and perhaps a little bit of angular momentum algebra and hydrogen atom, you have seen those things anyway in different occasions. But probably you haven't seen that much on the quantum mechanical gauge problem. So I'm not going to skip that, and I'll try to pack it into 3 hours package. And we'll do that, and from then on, we'll start a new chapter that is the angular momentum quantization and angular momentum algebra and representations, and so on, an addition problem perhaps. I think that will take us to the end of the semester. We have, I think, either 4 or 5 weeks. That's sufficient. If need arises, we may squeeze in a couple of hours perhaps, but I think I'll manage to finish the program I had at the back of my mind and advertise at the beginning of this semester. I think that's a good point to stop now.